Hi, folks. Here's a lecture recording about chapter 23 in the Young and Friedman text anyway, which is about electric potential. But I want to start with something much more familiar. I want to start with conservative forces. There were, back when we first encountered them, two conservative forces. The force of gravity, the elastic force exerted by a spring. Now, just for memory's sake, I'd like to remind you that there were four properties of conservative forces. The first, perhaps most sort of associatedly with the word conservative, we can represent the work done by a conservative force as the change in a potential energy function U. Two, it is reversible. Friction, for example, is not reversible. It always does negative work. We can't turn this around. We don't get back to where we were. It is independent of the path that we take to get from point A to point B. It doesn't matter how we change the height of an object. We could take it to the moon and back, and as long as the change in height relative to the Earth is the same as just taking it and lifting it, we're talking about overall the same change in the gravitational potential energy of the Earth object system. And that's worth stressing. It's not the coffee mug. It's the coffee mug Earth system that has potential energy. In a closed path, we start and we end at the same spot. However we did that, the work done by the conservative force is zero. These are the four things that are true of conservative forces as we defined them back in 231. The gravitational force, which at least in the Young and Friedman text wasn't defined until later, capital G, some strength constant, m1, m2, divided by the square of the distance between two masses, between their centers of mass, and attractive, always, directed along the line between them. And that, for all of 231, was our go-to conservative force, gravity. I'd like you to consider, though, the Coulomb interaction. If the charges are of the same polarity, then the product will be positive and it's repulsive. If the charges are of opposite polarity, then the force is attractive and the product is negative. Still directed on the line between them. Directed on the line between them. All right. The only difference that attractive versus repulsive, like now there are two cases, all it does is introduce a minus sign to the direction of the force. And here's what I'm saying. If this was a description of a force that was conservative back in 231, that same description had better be conservative now. If it's defined the same way, all right, yeah, sure, it's different, different pieces. It's a different constant. We're talking about charge instead of mass, but they're analogous, right? Like mass is a scalar quantity intrinsic to matter, so is charge. The separation distance is the same, and it's still directed along the line between them. If it was conservative before, it's going to be conservative again. We're going to be reasoning by analogy a lot in this chapter. It starts now. Okay. So keep that in your mind. The Coulomb force, the electrostatic interaction between charges, is conservative. Let's talk about electric potential. A preview of what we plan to do this chapter. Pause the video, take the time to read it. I'm not going to read it to you. Electric potential energy is hugely important. Wait, energy? Yeah. The meat and potatoes of this chapter is actually energy, even though it's called electric potential, because electric potential is our go-to. That's our, remember how much energy conservation simplified problem solving back in 231, right? If we were talking about forces or momentum, we needed vectors, we needed components, but as soon as we switched to talking about energy, it's scalar, and all we have to do is talk about, is it conserved or not? And even if it's not, all right, so we'll talk about the work energy theorem, which works either way. It's great. So we'd like to get an electrical analog for that. And okay, let's electrical potential energy, just like we had potential energy for energy conservation back in 231. The work done by the field is independent of the path the particle takes. We could prove it, but we don't need to, because we already know the electric force. Now, the field, right? That didn't work. The field is just a scalar multiple away from the force. So the electric force that we're talking about is the electric field that's pushing this charge is conservative. Okay. So we can happily define a potential energy change because we're talking about a conservative force. The force is the charge times the field, and work is force times distance. Okay, so we multiply the force times the distance. Ta-da, work. And negative change in potential energy. In a gravitational field, I warned you that we were going to reason by analogy a lot. In a gravitational field, we drop an object and it moves to decrease the potential energy of the system. That's how objects move subject to gravity. They try to reduce their potential energy in that configuration. Positive charges are no different in an electric field. It will move to decrease its potential energy. It's negative. The potential energy change associated with the amount of work, if we solve for the potential energy change, it's negative. It's associated with a decrease in potential energy because that's the way the field wants it to go, just like a falling object is affected by the way gravity wants it to go. The field does positive work, so just like when gravity does positive work, the gravitational potential energy of the configuration decreases. If we go the other way, we are doing work against the field and the potential energy increases. Think about the non-conservative version of the work energy theorem. If non-conservative work is done to move the charge opposite the direction that the field is trying to push it, the potential energy should increase. Now, the story is a little bit more complicated than for gravity because we have two different kinds of charge. We only have one kind of mass. So if it's a negative charge in a uniform field, if a negative charge moves in the direction of the field, the field is doing negative work. Because of the dot product. The force of the field is QE. And in this picture, it's down. Dot. The displacement is down. Those are in the same direction. What do you mean it's negative? But Q is negative. So this ends up actually being a negative quantity. And if the work done is a negative, then the potential energy increases. If a negative charge moves opposite the direction of the field is doing positive work, and that's associated with a potential energy decrease for the inverse reasons. Since the electric field is doing work that is independent of path, the electric potential energy only depends on the distance between 2 points. if we're talking about the work done on one charge by the electric field due to another, okay, fine. It's the work done by an electric field. It's path independent. And all we care about is where the two charges are. What is their separation? Because that's the line along which the force acts. A test charge moves from A to B on arbitrary paths. Don't care about the path. All that matters is how far away are we now? How far away are we then? If this is a positive test charge, if Q0 is positive, then we're moving farther away from positive charge Q, which means we're moving in the direction the field wants us to go, which means delta U has decreased. And the work done by the field is positive. If the charge is negative, the story's backwards. If the charge is negative, it's attracted to the positive charge Q. So moving farther away is opposite the direction that it wants to go. Somebody had to do some work to do that. And we've increased the potential energy. The electric field due to charge Q is doing negative work. Well, wait then. The electric potential energy associated with 2 point charges depends only on the distance between them. Okay, so let's write that. The electric potential energy of 2 point charges depends only on the distance between them and their actual charge. One charge sets up the field, and that field interacts with the other charge more strongly. So whoever sets up the field depends on their charge, and whoever reacts, it depends on their charge as well, because however much they are charged, that depends, that affects how much force they feel. This equation is valid no matter what the signs are. If they are the same, then so like charges, the potential energy is positive. Opposite charges, the potential energy is negative. Set one positive charge and one negative charge next to each other, they will attract. It's like if we fix one of them and release the negative charge, it's trapped, it's bound, it's in a potential energy well. To keep it where it is, we have to put energy into the system. Otherwise, it's going to fall. It's going to fall towards, just like a mass would, towards the earth. But if that other charge that we release is a positive charge, well, then it's going to get pushed away. It's going to fall away from the positive charge unless we put some energy in to hold it there. In either case, the farther away the particle gets, the closer to zero the potential energy becomes. Note the dependence 1 over r. The farther apart they are, the less the potential energy of the interaction between them. Makes sense. If a positive charge repels another positive charge, the farther away it gets, the weaker the field. The weaker the field, the less any particular displacement is associated with work. So smaller work, smaller potential energy. We're getting close to zero. We have some pictures. If we're talking about like charges, then think back to when we discussed in 231, when we discussed the, van der Waals forces and the oscillations of a molecule. There's an equilibrium separation, and we looked at a potential energy diagram, kind of like this one. The difference was that there was a minimum, and then we asymptotically got to zero. Push them too close, the potential energy is positive and they repel, just like two positive charges, because the nucleic interaction takes over. Have them too far apart, they don't really interact. Maybe there's a little bit of attraction. A little bit of attraction. Get them closer and closer and closer together. There is an equilibrium separation between them that has a minimum potential energy. So you're familiar with this idea, but there's no minimum here. One positive charge just will push another one away. And there's no equilibrium separation. We have one charge fixed, the other one is going to run away as far as it can go. Now, here, again, there's no equilibrium separation. Release a negative charge somewhere near a positive charge, there is some small potential energy of interaction, close to zero. It's attractive because it's negative, which means that negative charge, even though it's really, really, really far away, technically is bound by its attraction to that fixed proton. The closer it gets, the more trapped it becomes. Only as R goes infinite in either case does the potential energy of that configuration, not of one charge or the other one, but of the two of them as they are, only as the separation distance goes to infinity does the potential energy trend to zero. Could we do this with more than one point charge? Sure, why not? We can superpose the forces. Okay, so we'll add up the forces, which means we're adding up the potentials. The potential as experienced, the electric potential energy associated with this charge in a configuration with these three. Okay, so this charge in configuration with these three from I equals 1 to 3. If there are more, great, then there are more. This is not a new idea. We have already defined let me say this in words. We defined the electric field a couple classes ago. Three-line equals is defined to be not equal for any other reason, but it's equal because we say so. Force divided by charge. In other words, force per unit charge. The electric field is a question, how much force does a charge of magnitude Q feel in this environment? F. All right, how do we quantify that? Let's find the ratio. How much force do you feel? Divide by how much charge do you have? Because if this other charge has a different charge, it's going to feel less force, but you're both in the same electric field. All right, so let's talk about the fact that your environment is the same, even though you're experiencing different forces, and it's electric field that does that because we're scaling back by, okay, you're part of the equation, but what equation are you part of? What is the environment in which you're participating? How much force do you feel per unit charge that you have as opposed to this one? Okay, so if we can talk about force per unit charge, why couldn't we talk about potential energy per unit charge? After all, force and potential energy are related, right? Back very, very early on, when we were talking about vectors, right? We talked about the gradient. In the vector math recitation, we remembered the gradient operator, and that's how force and potential energy are related. So if we can talk about force per unit charge, why can't we talk about potential energy per unit charge and take the gradient of that instead? All right, let's do that. Let's define electric potential. Potential energy per unit charge. Because talking about potential energy requires both charges. The charge that sets up the field and the other charge that experiences it. Just like the electric field. Talking about the Coulomb force requires one charge to set up the field and the other charge to experience it. So we scale by the test charge that experiences things and just talk about the environment set up by the one charge. Same story here. A charge Q has a potential energy at this spot in configuration with this environment as set up by these other charges. Okay, so let's define potential per charge, scaled by what charge it is that's experiencing the electric potential energy environment, electric potential energy environment as set up by the other charges in the vicinity. The symbol we use for electric potential is a capital V. Whoa. Because another name for electric potential, or often just potential, is voltage. And in fact, the unit for potential has the dimensionality of joules, or has the units of joules per coulomb. Which I'd like to define as a volt. After Alessandro, I think, Volta, who is credited with stacking electrochemical cells to create a battery of electrochemical cells, redox reactions in series to achieve greater potential energy per unit charge, greater voltage. The potential of A with respect to B, the potential of A with respect to B. We at A turn around and look down to B. Where are we relative to where that is? And the answer is we are 1.5 volts, 1.5 joules of potential energy per coulomb greater than point B. the potential energy that a charge existing at point A would feel is 1.5 joules per coulomb of its charge greater at A than B. So we say that A is at a higher potential than B, or that there's a potential difference V sub AB between those 2 points. The work done when a unit charge moves from A to B. The work done per unit charge. A little bit ago, we said work had the general form QED. If we divide by Q, because we're talking about per unit charge, and work is potential energy, then we're saying that potential energy has something to do with QED, at least in magnitudes. And if we divide by Q on both sides, the electric force when a unit charge, in other words, Q is 1, moves from A to B through the distance D. We had already defined the electric potential energy of one test charge Q0 in an environment in a configuration with existing charge Q. So we divide away the testing charge Q0, and we end up with that. The electric potential due to a point charge. If there are many charges that make up the configuration, so okay, fine, we add them all up. If you move in the direction of the electric field, the electric potential decreases. If you move opposite the field, the potential increases. Per unit charge. How is this slide a thing? Isn't there a second case when the charge is negative? Hold on, let me go back. It depends, right? Which two charges are we talking about? If the test charge is negative, then the change in potential energy is positive. If the test charge is positive, then the change in potential energy is negative for this particular path from A to B. So how does that, wait, how does that work with this slide? Charge Q in this case is positive. as we move away from the positive charge. If we are a positive charge, that's the way the field wants us to go. So two positive charges, as we get farther away, the potential decreases. The potential energy decreases. So we're happy to say that V, which is potential energy per unit charge, also decreases, because if U is decreasing and we divide by the positive charge, yep. What if Q0 is negative? Now, a negative charge moving away, moving outward from the positive charge. The product of the charges is negative, so the potential energy is negative. As we move farther away, R is increasing, which means our negative potential energy is becoming smaller in magnitude, right? This is a constant, so ignore that. The numerator is negative and permanent, right? If we're talking about charge Q and charge Q0, the numerator isn't going to change. As we get farther away, the electric potential energy, still negative, becomes smaller in magnitude because we're dividing by a number that is increasing in size. A negative number becoming smaller in magnitude is increasing. On that previous slide, we said that if the test charge Q0 is negative, that the potential energy change is positive, and it is. But the potential energy itself of the configuration is still negative. Okay. So what does that have to do with the potential? The electric potential. Same equation. If U is negative, but Q0 is as well, then the minus sign is going to cancel out. And we're going to end up still with a positive electric potential that is decreasing. Why positive? Because it's due to a positive charge. And it's decreasing because the magnitude of U is decreasing. When we divide by the negative charge Q0, it becomes positive, but the magnitude of that result is still going to decrease as we move farther away. We only need one slide for electric potential because it's potential energy per unit charge, and we divide away the dual, like the fact that we need two versions of it, one for positive, one for negative. We're scaling away from that. It's more fundamental in a certain sense than potential energy, because it doesn't matter what the test charge is. The electric potential is what it is due to the charge that we're fixing. Or wait a minute. Where did this equation come from? Same place it always does. The change of potential energy is the negative of the work done by the conservative force. And the work done by the force, by definition, is the path integral of that conservative force along some displacement from A to B. Divide the whole thing by Q. Force per charge, that's electric field. You don't want to call it dr. You want to call it dl, the length along some path. Fine. But that's still got to be true. Wait, hold on. Let me go back. I missed the minus sign. The work done is force.dl. But the change in the potential energy is the negative of the work done. I need that negative sign. This still isn't right. This isn't delta V. Not from A to B. So what's the problem? Why is there an inconsistent minus sign? But check the limits. The limit switched. And check it out. We're not going from A to B. We're going from B to A. And the reason for that is how we looked at that battery symbol earlier. The potential at A looking down the battery at B. The potential at A from B to get to A, we needed to do a thing. Potential energy at A relative to B. And we're asking the same question here. Potential energy at A relative to B. Where are we now versus where were we? We are talking about the potential at A relative to B. Yeah. Everything lines up between this slide and the notes document. So, in order for the dimensions to work out, the left-hand side has the dimensions of volts. The right-hand side has the dimensions of electric field, newtons per coulomb, because force per charge, times meters. So we could also equate newtons per coulomb electric field to volts per meter if we divide both sides by m. It's charges that we're moving. We could define another unit of energy. Volts are good, but if we're moving individual charges, the charge is in 10 to the negative 19 coulombs. 10 to the negative 19. That's a ridiculously small number. So maybe if we're moving individual charges, maybe it makes sense to define a new unit. This equation just comes from delta U. Okay, cross multiply by Q. Again, electric potential is potential energy per unit charge. Okay, cross multiply, and here we are. If the charge Q in question is the magnitude of the electron charge and the potential difference we're talking about is 1 volt, then the energy change associated with that is defined as an electron volt. 1 electron volt, by definition, is 1.6 times 10 to the negative 19 joules. Well, because if it's 1 electron, Q is 1.602 times 10 to the negative 19 coulombs times 1 volt is 1.602 times 10 to the negative 19 joules. Well, that's going to be an awful lot of writing, 1.602 times 10 to the negative 19 and multiples of it. Let's save ourselves the trouble. One electron volt. Electron volt is not a unit of potential. It is a unit of energy. It is equivalent to joules, not to volts. Each electron in cancer radiotherapy has a kinetic energy of mega electron volts. 10 to the 6 electron volts. Each individual electron. Now, if we're talking about a conservative relationship, the potential energy of an electron through a voltage difference, a potential difference, should be related to the kinetic energy the electron has on its way out of that particular interaction. The potential energy we had to begin with related to the kinetic energy we have now that we have no potential anymore. What kind of electric potential is needed to talk about electron energies in mega electron volts? If we're talking about 10 mega electron volts, that's 10 to the 7 eV. So we did each electron, each individual electron. So this Q is 1 electron. So we divide both sides by Q, 1 electron. That's going to cancel out the E in electron volts, and the potential difference that we're using to provide these electrons this kinetic energy is 10 million volts. We've talked about the fact that the electric field inside a conductor is 0. Okay, so we can graph the electric field of a solid conducting sphere of radius r. The electric field is 0 inside, has some value at the surface. And then, because remember, Q over 4 pi r squared is sigma. That's the surface charge density. So this sigma over epsilon, and we're going to decrease as r squared away from that. Electric potential. In order for the field to be 0 everywhere inside, we're going to integrate 0. That's going to get us 0. So the difference, VA minus VB, the electric potential difference between any 2 points inside the conductor has to be 0. It's all at the same voltage. And it's all at the same voltage according to the voltage it would have just at the surface. Because we know from our work with Gauss's law that the spherical conductor outside the surface behaves like a point charge. So the electric potential at a distance r should look just like that for a point charge. And it's going to have that value the whole way. And then after that, it varies like 1 over r. As we get farther away, the electric potential decreases. Electric potential is important for real applications having to do with lightning rods and Van de Graaff generators and toner cartridges. If you've ever experienced an electric shock reaching for a doorknob, you have experienced the ionization of the air between your finger and the doorknob, because the potential at the surface of the doorknob is related to its radius and the electric field at the surface. And if the electric field at the surface is large enough, the air can ionize and allow the conduction of charge. The electric potential between 2 parallel plates has to do with how far away we are away from the negative plate. As we start at B and move up towards A, we have to do work according to our Y coordinate. Work and potential energy are related. So we divide by Q, and then we're talking about electric potential. Dividing by Q means we just have EY. in a gravitational environment, not unlike this one pictured. Not every mass at the same elevation has the same gravitational potential energy. If we put different masses at the same altitude above the surface of the Earth, their their gravitational potential energies in that configuration might be different because they have different masses. But if we talk about gravitational potential energy per unit mass, they'll all be the same. Per unit mass, we need to know the gravitational constant, we need to know the mass of the Earth, and we need to know how far apart the center masses of the two objects are. And that's it. There is a gravitational potential that we could define just as well as we defined an electric potential. All the objects the same distance away from the center of the Earth are experiencing the same gravitational potential. Drawing a line between the locations of all objects the same distance away from the center of the Earth means elevation lines. A line that collects all the points in altitude above sea level, which corresponds to a distance away, the same distance away from the center of the Earth, from the center mass of the Earth. Put any mass you want somewhere on this line. Its gravitational potential energy will be different, but its gravitational potential will be the same. All right, so let's do the same thing for electric potential. An equipotential surface is an elevation line for electric fields, for electric potential. Put a different charge on this equipotential contour. Different magnitude charges will have different potential energies in this configuration, but scale by their charge, they'll all be experiencing the same electric potential due to our positive charge. Field lines and equipotential surfaces are mutually perpendicular, always. Why? If we're here, at something just more, it looks like maybe, I don't know, 1900 or something. Just more than the contour at 1800. Make this terrain perfectly smooth and drop a marble. Which way does it roll? it rolls in the direction that the terrain changes most steeply. Find the direction in which the equipotential contours are closest together and go that way, because that's the way the ground changes most steeply. And the little line segment I drew is perpendicular to all of those equipotential contours, because gravity wants you to fall as quick as possible. The line that represents the net force that you feel on this terrain as a result of gravity is that line, because that's the way gravity wants you to go. That's the way the gravitational field is exerting a force on you. And it's the same kind of thing. It's the way that the electric force is exerting a force on a test charge, a test mass, a test charge. There's no preferential direction here. We could roll off in any of these radii, but we're going to roll away from that positive charge. We could draw contour maps like an elevation map for an electric dipole, for two nearby positive charges. Now, remember, the electric field just outside a conductor is perpendicular to the conductor. And the surface of a conductor, in order for all the points within a conductor, hold on, let me go back to that page. All the points within the conductor, including at the surface, are at the same electric potential. Otherwise, the field inside wouldn't be zero, and we know that it has to be. So the surface is another equipotential line. And as we move away from that positive charge, we would start to see those equipotential contours flattening out here, perpendicular all the time to the field lines. If another proof, a better proof, a less arbitrary feeling proof that the electric field just at the surface of a conductor has to be perpendicular to that surface. If there were a tangential component, we could contrive to move a charge in a loop like this and experience this tangential component of the field doing positive work. We could net work done in a closed loop by an electric field, which in order to be an electric field, it's got to be conservative, and this ain't it. It's not possible. We can't have this situation, because if we could, then the electric field wouldn't be conservative. This is hardly a surprise. I mean, it was there. It was there all along. F over Q, that's E. U over Q, that's V. That's all. I mean, it was there. It was there all along. This is not a shock at all. Force per unit charge should be the negative gradient of potential energy per unit charge, because force is the negative gradient of potential energy. We gotta have it this way. As soon as we defined electric field, we were stuck. We were headed this way. But wait, that means if we can figure out the scalar electric potential associated with a charge configuration, then all we've got to do is take its gradient and we know the electric field. Yet another way to evaluate a vector electric field using a scalar idea. No, it's not going to let me draw here. Oh, wow. Sorry about that. We said just recently, the Gauss's law lets us talk about the field in terms of a scalar. And the same is true here. Here, we can talk about the electric field in terms of a scalar. Or vice versa. If we know the electric field, we can talk about the electric potential. And as soon as we can talk about the electric potential, that makes problem solving much nicer. Just like it was nicer when we talked about conservation of energy instead of momentum and kinematics, because we didn't have to worry about vectors anymore. It's sort of striking how similar what we're doing now feels to what we did in 231. It didn't start out feeling that way. I mean, the stuff the other day with the divergence, that's way out there, but we're using the same equipment. Really kind of remarkable that we're able to do that. Okay. I'll end here.